Cosmology and Consciousness. Three very interesting talks. It's a great pleasure and honor to introduce the first speaker, Ivette Fuentes from the University of Vienna and also University of Nottingham, who will speak on gravity in the quantum lab. Let's welcome Ivette.
So, well, I'd like to thank Stuart and James and Eric and the organizers for this fantastic invitation. I actually feel in a superposition of feeling a bit uncomfortable about coming here and giving a talk that doesn't have anything to do with consciousness. But I hope that in my talk, at least you manage to see that it might someday touch with it hopefully in some way. And I feel very good about being here for a very funny reason. And that is when I was a high school student and I had to choose what I was going to do with my life, I had very clear, which I think it's a bit rare at that age, what I wanted to do. So I knew I wanted to do research, and I also knew that I wanted to understand how thought and consciousness arise from the interaction between atoms or neurons or whatever was going on in the head, in the brain. So I went on and I asked my family and I asked my teachers, what should I study? I want to answer this question. And they really didn't know how to guide me. They told me, well, my aunt's are a psychologist, my aunt is a doctor, my father studied physics, and in spite of that, they were puzzled. A little bit, why would you want to answer that question as well? They were puzzled with that. But they said I should study medicine, but I was like, no, I don't think I can go and operate on people and things like that. I don't have that kind of, sort of strength. And psychology, I thought, well, that maybe is more about behavior. Eventually, I gave up, and I was a bit disappointed about it. But I thought, okay, I'll study physics, which is very interesting anyways. And maybe in the future, I find a way to get back to that question. Then I did a PhD in quantum information. I had already forgotten about my interest in that. And once I finished my PhD, I was preparing a public lecture, and I wanted to explain to people from scratch what is quantum information. And I used as an example computers, normal classical computers, and the brain in order to talk about quantum processing. And then I realized, as I was giving my talk or preparing it, that I had learned a skill and I had learned things that could be useful, perhaps, on understanding the physics of the brain. I thought maybe there are quantum effects in the brain. And now that I know how to process information using quantum systems, maybe one day in the future, I will be able to actually address the question I was interested as a young student. But again, this was 2005, perhaps, and I went on to study, to work in the overlap of quantum information, quantum metrology, and general relativity, which is what my talk today is about. And, well, the work that I did there drew the interest of Roger, and he eventually invited me to be one of the founders of the Roger Penrose Institute because of my proposals on how to measure gravitational effects using quantum systems. That's what I'm going to tell you about. But from Roger's proposal is that Roger thinks that consciousness arises where quantum mechanics and general relativity meet, and actually where quantum mechanics goes wrong. So maybe the work that I do will have to do something with consciousness in a few years, and maybe you find me again in this stage talking about consciousness. But for now, please excuse me, and I'll have to stick to what I really know. Thank you. Thank you. So we live in the classical world. That means that our scales of space and time are compatible with, say, the laws of Newton. So we live 100 years and we measure, let's say, 2 meters. And then we see objects move like cars at, 200 kilometers per hour and so on. So at that scales of space and time, the world can be well described by Newton's equations. And when we go to school, in high school, and we learned about classical physics, we're kind of very comfortable with it because it's in harmony with our experience. Our brains evolved perceiving these sort of scales of space and time. And although sometimes we might be lazy with the mathematics or we might not like the mathematics, the concepts that we learn of classical physics are very intuitive and natural to us. However, if we go to very, very small length scales where atoms live, so these are different space-time scales, then classical physics doesn't explain the world there anymore. It's quantum mechanics that describes nature at those scales. And very strange things happen quantum mechanically. But strange, I mean, we find it strange because we don't perceive the world in the way quantum mechanics behaves. So quantum mechanics tells us things like, for example, electrons can be in many places at the same time. Well, we're not very sure about that. Our mathematics say that, and you can interpret it in that way. That's why we also have an open question with the interpretations of quantum mechanics, because we're not very sure of that. But clearly, the world behaves different at quantum scales. And it's different in a way that we can't really understand it if you try to understand it with these classical physics, classical pictures that we have when you learn about an apple falling and so on. Now, if you go to large scales, where galaxies live, where planets live, and so on, then also classical physics fails to explain nature at these scales. In this case, we have general relativity. And again, the physical effects that occur in general relativity are non-intuitive to us, and again, they feel strange. So the perfect example is time dilation. So clocks tick differently for different observers. The state of motion of the observer will give rise to different clicking of the clocks, and then you might have some traveling observers being younger or older than others, and so on, which is also something that we don't see in the world. So something which is fantastic is that mathematics has allowed us to explore these worlds that are so far away from our own scales of space and time. It's thanks to mathematics and theoretical physics that we can start first in this theoretical way, asking questions and proposing models of how nature would behave with atoms and so on. So I really find this fascinating, that we're able to explore these worlds that are very far away from us. And we're living truly very exciting times because we're at the brink of seeing quantum technologies. So all the technologies that we have today are the children, let's say, technologies of classical physics. As crazy and exciting as our technologies are, for example, the internet or all our gadgets and so on, they use the laws of Newton to operate. Some of them, and we call those quantum technologies 1.0, have components like computers, transistors, that actually are quantum components, but we don't use the quantum properties like entanglement or squeezing actually to compute or transmit information and so on. If you do, then that's called quantum 2.0, and that's what we're about to see. So you already had some talks yesterday by Harmut, for example, and so on, who's building a quantum computer and so on. There's a lot of progress being made in that direction. There's huge investments all over the world because I think we're all pretty much aware that we are at the very beginnings, at the birth of the quantum era. That makes me very excited because just to think about the technologies, I mean, the technologies that we have right now are the technologies of the world that is in harmony with our experience. And we're about to bring and materialize the technologies of this tiny little world that we can't see. And I just can't wait to see where that takes us. But you see, we're leaving behind the other side, the world of the big, general relativity. I don't know of technologies actually that exploit general relativistic effects. And I always think that it's a bit like trying to run a race using one leg when you know that you have two. Nature is quantum mechanical and general relativistic as well. And I think that we should be making same efforts to exploit the relativistic effects so we can take the technological revolution even further. So this is what I've been trying to do for several years with my group. We're working in exploiting relativistic effects as well, or at least using theories, and I'll tell you about these theories, theoretically, that will allow us to start proposing technologies that operate in the overlap of quantum mechanics and general relativity. So quantum mechanics and general relativity are the most fundamental theories that we have of nature. And they both have been extremely many times corroborated in the experiment in their different regimes of applicability. So we know that there's something very correct about these two theories. However, they are incompatible. We don't know at space-time regimes where we might expect both quantum effects and relativistic effects to be present, we don't understand physics there. We don't really have theories. So, for example, that's the main aim of quantum gravity. In quantum gravity, people start with general relativity and then go to very small length scales where we would expect quantum effects to take place. And there are several candidate theories, like, for example, string theory or loop quantum gravity. But so far, there is no consensus in the scientific community that any of these theories succeeds at explaining the overlap of quantum mechanics and general relativity in a consistent way. And I think that the problem and why this has been so difficult is just because we don't have experiments. I mean, imagine that there is a black box and you want to describe what's inside the black box, but you just can't do anything with it. You just have to guess. And if you see what string theory and loop quantum gravity have been doing is a bit of that, is guessing and developing fantastic mathematics, but there's no physical predictions. And if we see from the history of science where we made the most progress is when we have this feedback between theory and experiments. So I think that this is really a big problem with quantum gravity, that we haven't been able to do that. But something fantastic is happening. Again, you know, times are getting very exciting because quantum experiments are developing so fast. And that's what I'm going to tell you in the next slide, that they are reaching these regimes where we will start seeing relativistic effects as well. So I think this will open very important possibilities and will really, if we're able to make these experiments and get results from them, we will be able to understand a lot more about nature. So yes, so I'm very excited to be able to stand here and say that the quantum era is reaching relativistic regimes. And this is because when I did my PhD, I did it in quantum optics at Imperial College. When I got there, people said the information era is reaching quantum regimes. So we need to take into account these 3 points: physical aspects, practical aspects, necessary corrections. If you're sort of trying to figure out how to compute, say with classical physics, but now your components are at the quantum scales, you're going to be making mistakes. Now as well, if you want to do quantum information, but your components are somehow at a relativistic regime, you have the wrong underlying physical theory and you will have mistakes. So that's kind of the boring part of things. Much more interesting is innovation and new technologies. Okay, now that we accept that we need to upgrade our underlying physical description of the world, what can we do new? So the example in quantum technologies was, well, if we're going to have computers or be able to transmit information using quantum systems, well, then we can teleport, or we can do quantum cryptography, which were things that you cannot do in the classical world. So if we're going to be able to bring together quantum effects and general relativity, I think we should be able to generate new technologies that would not be possible without relativity. And this is an important part of my research. But the most interesting thing for me is the last part, fundamental aspects. In this whole boom of quantum technologies and with the aim of building a quantum computer, we've learned a lot of physics. We learned a lot about decoherence, we learned about entanglement, and so on. And this is really what is important for me. So what I believe is that if we're able to have experiments and build technologies, and then use these technologies to learn about the physical world, we will be able to make a lot of progress. So when I started to work in the overlap of quantum information and general relativity, a lot of people told me like I was being crazy. Why should we do this? We're just starting to understand what quantum information processing is. Why should we worry about relativistic effects? And I was saying, well, on one hand, nature is both things. It's quantum mechanical and general relativistic. But look at the experiments. Every single implementation of quantum information uses photons. And there's no such thing as a non-relativistic approximation to a photon. A photon is a relativistic object. And of course, you can use aspects of the photons, like the helicity, which is not relativistic, and we know from the experiments that this works very well. However, I always felt that we were missing the opportunity of exploiting those relativistic aspects as well. But since then, life has made my life very simple, because these experiments, this is around 2005 when I started to work on this area, and then these experiments developed so quickly that Anton Zeilinger in 2011 managed to distribute entanglement across 144 kilometers in the Canary Islands. So you see things are getting bigger. In 2014, the group led by Paolo Villoresi in Padua made the first quantum transmission in space. So what he did is that he prepared some light state, a wave packet here on Earth, and he sent in a quantum state, in a squeeze state, and he sent it to a satellite, and then the state was reflected in a mirror and detected back on Earth. So he didn't distribute entanglement yet, but he did do a transmission of a quantum state with a satellite. And this was at 2,600 kilometers. Last year, the Chinese group launched the first dedicated satellite for quantum technologies. And already a few weeks ago, this satellite started making transmissions. They're the first steps. I don't think they're quantum transmissions yet, but we'll move fast to that with an observatory that's in Vienna. And that's one of the reasons why I'm there, because I'm interested in proposing experiments to learn more about the overlap of quantum mechanics and general relativity, also using satellites. So we know that at the regimes where, where satellites operate, that relativistic effects start to kick in. We know that from GPS. GPS has a precision, I don't know, say around centimeters. I think mine is evil and usually points me out in wrong directions. But in order to have that precision, it makes corrections due to general relativity. It has to consider that. And I don't think it's a technology that exploits it. It's more like at the first stage, it needs to make corrections due to it. But we can already see that these effects become relevant. So if we're going to take our quantum technologies to space, it becomes interesting to ask the question, how does gravity, the curvature of space-time, the motion of the satellites affect our quantum properties, like entanglement and squeezing and so on? And this is something that we already have results. I have been working on that for a while. There are a number of experiments that have been, and projects, and some of them are taking place, some of them are looking for funding, and so to take quantum technologies to space. So for example, the Space Quest project, also led by Anton, aims at distributing entanglement globally, so it can be used, for example, for quantum cryptography and so on. Also, there are projects to take quantum clocks to satellites, because quantum clocks are the best way that we have of measuring time, and you know that time has important applications, measuring time precisely in almost everything. And there are also a number of projects that aim at studying quantum systems in conditions of microgravity and so on. So that's not the only way in which, this is moving slow, that quantum experiments are reaching relativistic effects. Also, experiments on Earth are reaching relativistic regimes. And that's, for example, rapid moving boundary conditions. So these are using superconducting circuits. When we think about relativity, we always think about things that move close to the speed of light. So there are nice effects, like, for example, the dynamical Casimir effect that tells you that if you have a very rapid moving mirror, you can excite particles out of the quantum vacuum. And this is an effect that is due to both theories. However, if you move the mirror as fast as we can, as fast as we move particles in CERN, for example, one would create 2 photons in the lifetime of the sun. So you can see how small these effects are. However, people are incredibly creative, and Pearl Delsing, which is at the University of Chambers, demonstrated the dynamical Casimir effect instead of using a mirror, using a field that acts as a boundary. It behaves like a mirror, but since it's a field, this can be moved close to the speed of light. So they moved the boundary at 1/3 of the speed of light, and they saw particles being created out of the quantum vacuum. But my favorite type of experiments, which are reaching relativistic effects, are due to their precision. So I told my relativist colleagues that I wanted to use quantum systems like Bose-Einstein condensates to measure gravitational effects and relativistic effects. And they laughed at me because they said, come on, I mean, in the extension of a quantum system, space-time is flat. You're not going to see anything. Well, what they're not taking into account is that quantum technologies are incredibly precise, and this is the best example. Dave Wineland in NIST got the Nobel Prize for his manipulation of single quantum systems like atoms. Showed he didn't get the Nobel Prize for this experiment, but it's very impressive. He took 2 atoms, which are quantum clocks, and separated them 33 centimeters, and he measured time dilation. And actually, his clocks are so good that now he can do this with a few centimeters. So basically, it's showing you that at a few centimeters, space-time is not flat. And what I will show you is the Bose-Einstein condensate is 10 to the 7 of such atoms. So you can imagine how precise we can get. And then we can start probing space-time at very, very small regimes. So quantum metrology is a research field that has developed in parallel to quantum information. The main idea of quantum metrology is to use quantum properties such as entanglement and squeezing to measure parameters of great interest. So for example, time, the measurement of time is a part of this. Magnetic field strengths, frequencies, temperatures, whatever. We're always, in all our applications, we're very interested in being able to measure physical parameters very, very precisely. And quantum metrology has been very successful because we can show that by using quantum properties, we can measure parameters much better than if you just use classical methods. So because of that, people have also become very interested in using quantum metrology and quantum systems to measure gravitational effects. If you're able to measure very precisely small changes in the gravitational field, you can find out where there's oil, for example, or minerals, or learn something about seismology. And from a fundamental point of view, you could learn if general relativity still holds at those small scales and so on. So there's these 2 sides, the technological side, but also the fundamental side, which is interesting. However, I noticed a few years ago that people were using quantum physics, Schrödinger equation, and then applying this to measure gravitational effects. So if you want to measure classical gravitational effects like Newton's gravity and so on, you're fine. because the Schrödinger equation and Newton's gravity are both invariant under Galilean transformations, the classical transformations of space-time parameters. However, if you want to measure something relativistic, if you want to measure the curvature of space-time or something like this, then general relativity is invariant under Lorentz transformations, and these are incompatible with the Schrödinger equation. So you can't just do anything like that. And then, again, we don't have quantum gravity. So how can we then apply these ideas in a consistent way? Well, we're very lucky because we do have an intermediate step, an intermediate theory, a semi-classical theory, that allows us to ask the first questions. And this is quantum field theory in curved space-time. So this is not still the full-blown quantum gravity thing. It's, as I was saying, an intermediate step. So basically, you consider that space-time is classical, and you put classical not in the Newton way, but it's not in quantum gravity. You try to think of space-time itself being quantized, and that's not the case here. It's just a background, and you put quantum fields on top of it. And then you see how changes in the space-time would create changes in the fields living, the quantum fields living in that space-time. And there's no back reaction. The fields don't curve space-time back. So that's why it's just an intermediate theory. But in spite of that, it allows you to ask first questions in terms of understanding part of physics where you would expect quantum effects living together with relativistic effects. And we are just starting to exploit the possibilities that this underlying theoretical framework will allow us to well, apply and develop technologies and also deepen our understanding of physics. And that's what I'm going to show you now. So I've been working with the Bose-Einstein condensate and giving it a treatment which is consistent with quantum field theory in curved spacetime, so the full-blown theory in that respect. So a Bose-Einstein condensate is, let's say, 10 to the 7 rubidium atoms. They are made of many different things. You can also make them out of sodium or lithium or so on. And they're cooled down almost to the ground state. So the temperatures are just fantastic. They can cool down the system to 0.5 nanokelvin. This is really amazing. So what happens at these very cold temperatures is that the wave functions of each atom overlap, and then the whole thing behaves like a big quantum system. So these are the largest physical systems that exhibit quantum behavior. The Bose-Einstein condensate itself can be as small as 1 micrometer or as big as 100 micrometers, for example. However, the whole physical apparatus can, you can put it in perhaps like a meter squared. So you need a vacuum chamber and you need some lasers and so on. So you can see it up there. That's my friend Jeff Steinhauer, who demonstrated Hawking radiation in an analog black hole in 2011 as well. And you know how computers are shrinking? We used to have computers that were like a huge building, and then we have been working towards making computers smaller and smaller. We're doing the same thing with experiments, with physical experiments, and with quantum technologies. So very soon, you will be able to have an experiment like that in a chip, and then you can put the chip in a nanosatellite, which is that big, and maybe send it to space and do experiments with that. They already put a BEC on space last year. Actually, even maybe it was this year, so that's already possible. So what can you do with a BEC, and why did Roger become interested in that? Well, one of the things you could do is test the collapse of the wave function due to gravity. So there's been an experiment taking place using mirrors, and still they haven't been able to demonstrate that gravity collapses the wave function. And well, we think that the reason for that is because the system is very hot. And when you have high temperatures, then there is a lot of decoherence, and then seeing this effect is very difficult. However, Roger and I have been working in proposing an experiment using a Bose-Einstein condensate, and again, because it's so cold, then it's much more stable, there's less decoherence, the system decoheres in a second, so we think that this gives us enough time in order to perhaps see the collapse of the wave function. In order to see it, you need like 10 to the 11 atoms. And this is still out of what people are doing right now. They can have BECs as big with rubidium, for example, 10 to the 7. But we're working on how could we maybe, I don't think they can put right now more atoms. It becomes very difficult. But then you can play with other parameters like the density and the size and so on, and perhaps we will be able to see this soon. So one of the aims of the Penrose Institute is to have an experiment like this and demonstrate at the perimeter. I'm saying that because I used to work at the Perimeter Institute, and now it's the Penrose Institute. So we would like to see at the Penrose Institute the experiments testing these regimes in the overlap of quantum physics and general relativity there for the first time. So that would be very exciting. So what else can you do with a Bose-Einstein condensate? Well, you can measure almost any gravitational effect that is big enough for its sensitivity. So I want to show you, for example, how could you measure gravitational waves using such a small system, and how this would lead to a really big breakthrough in what we know about the universe and cosmology and so on. So imagine the BEC. So there are these atoms, and maybe you want to picture it like coffee in a cup, or maybe like the ocean. So all these atoms form a bulk. And the bulk you can describe by a wave function that I call the mean field. This would correspond to all the atoms really being cooled down to 0 temperature. And that would obey a classical equation called the Gross-Pitayevsky equation. However, the atoms collide, so you can't just consider this mean field function. You have an extra correction to that, which is this pi, which are quantum fluctuations. So you can imagine this as little waves on top of the ocean. And those little waves are a relativistic quantum field, and they're quantized. And they satisfy a relativistic equation, which is called the Klein-Gordon equation, that depends on an effective metric. So this is the only equation I have here, but I just wanted to show you because I'm just very excited about it. So this GAB is the effective metric on which the phonons, it's like the effective curvature in which these phonons live. And then you see the GAB that I have with this arrow called the real space-time metric. That's the underlying space-time metric. If we have a gravitational wave or something like this, this would be the real thing. And then there's this other term, which I call the analog metric. There's a field called analog gravity. And what they do is that they ignore the real space-time metric because they have the same way of thinking, this must be very small, we can ignore it. And what they do is that they play with this analog metric to make, that depends on the parameters of the BC, to make it behave as if there was a space-time. So this is what my friend Jeff Steinhauer did to demonstrate Hawking radiation in the Bose-Einstein condensate, that he played with these parameters to make like a sonic black hole. But what we did is we said, why don't we do it the other way around? We make that flat, meaning imagine the ocean is very, very, very still. And then we ask the question, are changes in the real space-time metric, could those produce changes on these little waves living on the BC in such a way that we can detect them? And if we can detect them, then we can detect gravitational effects. But this theory here is consistent with both quantum mechanics and general relativity. So if we're able to take this theory to the experiment, we're doing the real thing, and we're starting to learn about physics at these regimes. So we first applied this to gravitational waves. This is very fashionable right now because I guess you all heard that last year gravitational waves were detected for the first time after 4 decades of trying. So general relativity predicts that you have an accelerated mass. So for example, you have 2 black holes moving one around the other, this would produce ripples in space-time. So this is like when you throw a stone in a pond and you get these ripples, only here the ripples are in space-time. And they were measured by LIGO, by a laser interferometer, which is huge. Each arms of LIGO are 4 kilometers long. And this is, of course, super exciting because it's the first time humanity sort of hears the universe. So I'll tell you a little bit that I will conclude with that idea. But the problem with these laser interferometers is that they cost around $1 billion. And well, there's 2 in the US. And because of the measurement of the gravitational wave, now they're going to build another one in India. And there's also plans to build one in Japan. However, with 3 or 4 points, you can't localize sources. So what does that mean? Well, imagine that you're in a room and you were blind. You could never see the universe in that way. And suddenly you open your eyes and you see light. I mean, that's already quite exciting, isn't it? But you can't localize. You don't know where the light is coming from. That means you can't resolve objects. The only way that we could start resolving gravitational waves is if we have many detectors. So how are we going to have many detectors if they're that big and they cost $1 billion each? We have to make them small, and we have to make them cheap. And we have a way if we use quantum matter in order to do that. And that's exactly what we've been working with. So we managed to make a proposal using a Bose-Einstein condensate and showing that little equation that I showed you to detect gravitational waves in this super tiny system. So more or less, it works like this. We take the BEC, which is like in a trap. So it's, let's say, imagine it's in a box. And we take the waves, these excitations that live on it, and we prepare a very sensitive quantum state, which is called a squeeze state. It doesn't matter what it is. It's just a very sensitive state of these phonons. Then the gravitational wave comes by. And the point is that the gravitational wave resonates with the detector. You see, LIGO is based on the change in the length of the arms due to the gravitational wave divided by the whole length of the arm, and that's why the arm has to be so long. However, in this case, that doesn't play a role at all. We're matching frequencies. The only thing that matters is the frequency of the wave and the frequency of the phonons. And the phonons are exactly in resonance with gravitational waves. That means that when the wave comes by, it shakes the phonons, and it creates some new ones, but it also changes them to different mode excitations. So we have super precise techniques to measure quantum states. So these are called state discrimination techniques. So if we're able to distinguish this change, then we measured the gravitational wave. So this is very exciting because everything that we know about the universe, about cosmology, about extragalactic objects, and so on, is through light. I did a bit of astronomy when I was an undergraduate student. Actually, my first paper is on Seyfert galaxies. And I remember that what I was most impressed was the fact that just we could know about chemical components, about velocity rates, about everything, just from photons, just from a few photons that we detect. So this is like humanity has been for many years now, well, not that many, but some years, looking at the universe with the electromagnetic field, with light, with our eyes. These are our eyes. And we've been able to do this because we build telescopes, right? So now, and telescope is something that allows you to localize. So now what we want to do is we put many of these detectors all over the world. We might put them on satellites. We could put them in satellites if we want. We might not need to. We could just put them on ground. But then we will be able to localize gravitational waves. So this means that we have a new sense. Now we can listen to the universe. And think about yourself, like when you're seeing this world, or when you're just hearing it, how intense it is to actually have sight and the ear operating at the same time. I'm very excited about this because I think that being able to do this will allow us to learn so much more about the universe that we're living in. So we build these technologies, and then what we do is that we start learning about the theories, right? So this is a bit like we build a telescope, then we discovered galaxies, and then we started to learn about cosmology, and so on. You first build the technology, you see, that's the point. That's the beauty of it. You build a microscope, then you start studying atoms. So this is what we want to do at the Penrose Institute as well. And it has many applications. You can measure space-time, estimate space-time parameters, proper times, proper accelerations, and so on. I want to build a probe to measure curvature using this. As I was saying, you can use it to detect local gravitational fields and find out where there's oil, make progress in our understanding of seismology, because we would be able to probe, to learn about the Earth as well inside of it, right? Because it's not only how we can look far into the universe, but we can also look into the Earth by doing this. So you can see it opens a lot of possibilities. Now, Roger also has a very interesting model for cosmology, where it's a cyclic universe. I'm sure you've heard of it, about it, and it also predicts certain behavior for dark matter. So some decay of dark matter and so on. And this is something that we would hope that this detector, which would also be able to detect and see if Roger's model is the right one as well. And you can also use it to measure dark energy and perhaps to find some new physics. So I want to end here just thanking my group, my postdocs, my PhD students, my younger students for all their help and work and insights and so on, as well as our collaborators. Well, very especially thank you all for coming so early and for being here. It's been a pleasure. Thanks.
Thank you, Ivette. That was incredibly interesting and exciting.
Thank you.
Congratulations. We have time for a few questions.
Hi, thank you. What frequency range was the BEC gravity wave detectors be able to detect?
Yes, that's a very good question. 10 to the 3 to 10 to the 4 hertz. So this is given by the size of the BEC. I said that the smallest ones that actually make sense, it's 1 micrometer. So this would give you the high frequency end, and 100 micrometers would give you the low frequency end. Now we might be able to change this if we do it with a different system. Right now we've been looking at rubidium and so on, but maybe one could even think about not using a Bose-Einstein condensate, but using liquid hydrogen and so on. We could then find other frequency regimes as well.
That's much higher than the gravitational waves already detected, correct?
Well, I mean, 10 to the 3 hertz is among what LIGO is detecting at the moment. And then we could go a little bit towards the higher frequency. LIGO becomes less sensitive in higher frequencies. So we could, I mean, we don't know what's out there. We don't know what's out there, yeah. So we want to go also to higher frequencies to see, yeah. Thanks.
Hi, Ivette. Thank you very much for that talk. It was beautiful, especially the way that you began and separated consciousness from the physics that you're talking about.
Thanks.
So you just said we don't know what's out there. My question is about how we think we know what's right here, and I'm the hand in front of my face. When I started studying high-energy physics at Cambridge in the graduate program, the first thing that they had us do was read a bunch of papers about phenomenology. And I didn't know what that was. What's phenomenology? What's phenomenology? It's just the basic data of the field. And so there's basic data about consciousness that it seems the physicists who are working in the area don't pay any attention to at all. And I'm really curious about this. It gives me great concern for the process of the field. For example, if I put my hand in front of my face and cross my eyes, the object bifurcates, which demonstrates to me that this is not the 3 space of ordinary matter energy. It immediately poses the question, if this 3 space isn't that 3 space, we've got at least, apparently, 6 dimensions right away. I mean, I can explain this to a high school student, but none of the physicists working in the area seem to pay any attention at all to this phenomenology that we can create just by talking with each other. We don't need to, I love what you're doing, and we need to do this. We need to probe these different scales. But why do we not admit the data that we can create right from our experience right here, that's data that's relevant to physics? It's dimension, you know, the simple, I mean, I have many, many more examples. That simple example translates into dimensionality, which is a very primary concern of the setting. I'm just very concerned about the process, and I wondered if you had any comments about the division of fields and the dialogue between fields and the admission of data, whether you see a concern there, and where is the place that this kind of dialogue can happen? I'm sorry, I went on a bit.
So when you say other scales, you wave your hand like this, and I think you're thinking about out there in the universe, right? But these devices allow you to test things that are between you and me, right? But that we can't, I think the point is that we can't see them with our eyes. But there are effects taking place between me and you that are distorting the gravitational field because there's, I don't know, there's dark energy, there's dark matter, there could be waves, all kinds of things. And, you know, sort of my day job is to build little devices to try to measure these things, but I'm not saying that that's the only thing that there is in the universe.
No, I get that, and I love that your work brings, you know, things to the terrestrial, but I'm having the same experience again. So when I wave my hand is moving around in your conscious experience, right? So when I'm waving my hand, I'm not pointing anywhere other than inside the experience that you're having. And there's data relating to the experience that isn't coming into physics. It's not admitted. In fact, that just happened right there in our conversation. It's not a criticism. I'm just pointing out that physicists operate within a mindset where immediately we move. I'm trained as a physicist. Immediately we move to the instrumentation, right? There's another instrument. There's another data set. It's right here. When I'm waving my hand here, I'm pointing in experience. And it seems incredibly hard to get physicists to admit there's a 3-space here. It's not obviously the 3-space that's part of the 4-space that we talk about in special relativity. As soon as you see that, it opens a theoretical inquiry right there that's just not happening. No one working in physics and consciousness is even taking that very simple data point into account. And
but
maybe
isn't that what Roger is trying to do? Yeah. This is precisely, I mean, at least in terms of the physics, I mean, maybe it doesn't satisfy you because you would like us to go much faster there, no? But one of the problems with science is that science goes slow, right? I mean, and now I think it's accelerating a lot, but it goes slow. And I think this is what Roger is trying to do by at least extending the physics of, you know, what we so far handle. So what he's saying is that if we want to understand consciousness, we need new physics. We need to go beyond it, because with the physics that we have, we're never going to be able to ask that question. So I think it's good that you try to understand these questions from different perspectives, but if you try to understand it as well from the physical point of view, I think this is the way to go.
Thank you. 2 more quick questions. First, I want to recognize Yvette's son, Leo, who has a question. Leo?
You said that, like, you thought that one day consciousness and physics would somehow meet. What exactly do you mean by that? And
Thank you, Leo.
And how do you think they would actually meet?
Sorry? Well, what I meant by that is that we all experience consciousness, every single one of us. And I think this is actually before we understand physics or we even think about physics, we're aware that we are aware, right? And this should be part of physics in some sense, because we experience it. And I was talking a little bit about how we experience space and time and the physical world that we see, and how we try to put this into laws. So we experience consciousness. So at some point, we should be able to describe it as a part of a whole.
That's what we're trying to do, Leo. You put your finger right on it. Oh, One more, please be brief, Nir.
Okay, okay. It was so interesting. So can you expand a little bit about the experiments of entanglement in the curved space? What exactly do we want to do there? You know?
Yes, actually, I started to work in the overlap of quantum mechanics and general relativity, asking questions about entanglement. So I didn't talk about that because there was no time. But I started to ask a question. Actually, my first curiosity along this line started because people say, okay, you know, how do you create entanglement? Well, Alice and Bob meet, and they have a spin 1/2 particle, and they created this entangled state, and then they move around, and they go to different stars, and they do teleportation. And I was like, where's the mathematics that describes that you separated them? I mean, does entanglement remains if the space-time is curved, if you move at relativistic speeds? What happens with entanglement? And then I started to do that's how my career actually started. I wrote a paper called Alice Falls into a Black Hole, which was very successful because I think the title was very catchy. But that's what I was trying to show, is that if you're moving, that degrades entanglement and so on. And now I have a new project in which we show that you can create a state that is disentangled, and then you just send it into space, but space acts as a crystal. Actually, it acts a bit as a beam splitter, which is able to entangle the state. So then I'm thinking a little bit more on the other way around, of thinking maybe in a quasar, some states were generated and they traveled to us and they arrived entangled, and we can learn something about the space-time through the entanglement.
Thank you, Ivette, for a wonderful talk.
Thank you.
A glimpse into the future, I would say. And it's a great pleasure to introduce our next speaker, Brian Keating, in the Department of Physics at UCSD and co-director of the Arthur C. Clarke Center for Imagination, who will speak on conscious cosmos. Let's welcome Brian Keating.
Thank you, Stuart. While I'm waiting for the handheld microphone, I'm a New Yorker, so I like to talk with things in both of my hands. Prevents me from using my hands in other bad ways. Stuart, don't go too far. I've got a lovely parting gift for you at the end. So make sure you stay awake. Okay, it's a great pleasure to be here. I've never spoken at a consciousness conference, and it's kind of hard to say. And I had a lot of deep anxiety, which might make me a good, either a true New Yorker, or it might make me, the perfect subject to study such questions, or maybe to ask questions and discuss things as an outsider. So that makes two physicist outsiders to start your morning with. If you're conscious and you've had enough coffee, you might be able to hopefully follow along, and if not, ask some questions at the end. So I changed my subtitle of the talk. I wanted to make it a little bit more astronomical, and in thinking about how we got to this conference, how we how we've evolved, and how remarkable it is that human beings essentially, and I'll try to make this case in my talk today, we're basically the most highly evolved form of the most ubiquitous thing in the universe, which is dust. So, the dust that makes up stars and planets, actually, without it, we wouldn't be here. That's about as out there as I'm going to get, okay? I'm actually going to do a lot of basically orthodox cosmology, and I'll explain to you what I mean. But in doing so, I came up with this subtitle, that actually perfectly encapsulates what we'll be talking about, and that's Twinkle, Twinkle, Little Star, How I Wonder What You Are, like a diamond in the sky, up above the world so high, like a diamond in the sky. I think. I don't know. I've got young kids at home. They know better than me. So that's the theme for today, and that's what I want you to think about and hopefully motivate to you how we know so little about the cosmos, but we're so ambitious as to what we do want to learn. And that, I think, is what's so remarkable about being a human being. So what am I doing here? Well, I was nervous, as I said, until I read the description that Stuart sent out, which was quite reassuring to me. And it said questions that will be explored are such things as, is consciousness intrinsic to the universe? Check. Okay, I'm a cosmologist. I know a thing or two about the universe. Okay, I start to feel a little bit better. Then the question of how did life and consciousness evolve? I might not be able to say too much about the latter, but the former I can speak to, and I'll in fact give you demonstrations that indicate with materials that I've brought here, the gifts that I'll be leaving with with Stuart that actually will help to perhaps motivate this theme of the Twinkle Twinkle Little Star motif today. Next thing that I want to talk about is how can consciousness causally affect Bryan processes. Is that what it says? I think. Okay, Bryan, that would be nice. Okay. Okay, I will mention the word brain, and I'll talk about a very outlandish aspect that in the cosmological model that is the dominant one, maybe not the correct one, but the dominant one, that seems to predict the existence of these exotic phenomena that have consciousness, the lowest form of conscious material or assemblage of matter called Boltzmann brains. So I will use the word brain in my talk. And then last but not least, do we have free will? This is a pretty big subject, right? And as a cosmologist, I can comment on this, and I'll discuss how it may relate to the multiverse and things like that and inflation. But I also thought I'm an experimentalist, so I build things in the lab like Ivette does. And so I was tempted to bring down from UCSD some experimental subject matter to actually study free will in real time. But then I realized these are my grad students, and I realized grad students are an existence proof of entities that have no free will, okay? So at least we know that there are entities that don't have free will. Maybe there are entities that do. So again, you sure you still want me here, okay? So Lev Landau, famous Nobel laureate, once said that cosmologists are often in error, but we're never in doubt. Okay, it's kind of a pejorative. He really didn't care very much for the dominant cosmology of the 40s and 50s, which was really, they should have been quite in doubt. And in fact, that's the most pleasant state to be in as a cosmologist. You don't understand what's going on. It means you're going to have likely to have employment the next day, because there'll be so many more mysteries to understand about the universe. Then I thought about, well, what do these you consciousness mavens think about consciousness? And so here's Daniel Dennett. He said, are zombies possible? They're not just possible, they're actual. We are all zombies. Nobody is conscious, not in the systematically mysterious way that it supports such doctrines as epiphenomenalism. And then he puts an asterisk. It would be completely desperate to put this without context. So I actually quoted the part that shows how desperately unintellectual I am. But it seems to me you guys that study consciousness are often in doubt, but maybe you're not in error, because some of the things that you're predicting may be flexible enough to accommodate a whole host of alternatives. And that's why the theme of tonight is going to be, or today, this morning. See, I'm still on last night's clock as an astronomer. I wake up early in the night and work all night. So I want to talk about the experiments that we do and how they falsify models, how they prove models wrong. Yvette talked about exploring models and maybe proving things. I like to think about the experiments I do as kind of the ultimate in disappointment. Okay, I'm a disappointment to many, and I hope to potentially disappoint Roger himself, because I'm looking at the potentiality of falsifying his otherwise beautiful, mathematically elegant theory, and we haven't done it yet. But it's always interesting to look at what can be falsified. And I think that winnows away a lot of the non-scientific things from scientific things. Okay, so then I Googled what's the most complex thing in the universe. And what do you find? Like 6 billion pages in 0.6 seconds, and it's the brain. Okay, so it says the brain is the most complex structure, and you can do this experiment yourself, all right? So I study the known universe, and I would agree the brain is probably the most, but I don't know that much about it, so that's why I'm here today to learn from you. I'd like to start now with some exercise, some physical activity. So I've shown up here that one of these pictures is a picture of a synapse, and the other is a picture of a simulation of cosmological energy and matter and their behavior after some amount of time. I want you to raise your right hand if you think that this simulation on the right represents the universe, or raise your left hand if you think the simulation on the left represents the cosmos. So raise your hand if you think the right side is cosmology. Okay, I'm raising my right hand just so you can show it. Raise your left hand if you think the right side is really the brain and synapses. Raise your left hand, okay? And raise your hand if you don't like raising your hand, okay? Because you got to get exercise. Okay, so the point is you really can't tell the difference. And I didn't game this. I mean, these are real simulations. This is the Millennium simulation on the right. It's the universe, and then it's a simulation of what a brain cell does during neural activity. Here's another thing that shows, at least superficially, that there's similarities between the cosmos and the conscious mind that inhabits our skulls. So on the left is a fMRI, and on the right is a CMB, a cosmic microwave background map. They look pretty similar, right? And people make all sorts of extrapolations from this, but it's kind of like a parlor trick, right? It doesn't really have any deep meaning to it. A lot of things can look the same but act very differently. But at its heart, what's so interesting to me is that the brain, in some sense, should be thought of, in some sense, as a type of computing instrument. And computers have aspects of them, as does the brain, that rely on ordinary physical, biological processes. Chemical processes are mediated not by quarks and gluons, they're mediated primarily by electrons and ions. So that's just chemistry, and chemistry, I shouldn't say just, but it's chemistry. Chemistry, Dirac said, is basically a consequence of his theory of high-energy particle physics. And so therefore, are the laws that govern the electrical conductivity in the brain, are those amenable just to simple application of Maxwell's equations? And that's they haven't really been supplanted, except at the quantum level, and we know a lot about quantum electrodynamics, the most precise theory in comparison to experiment that humankind has ever developed, with a theory and experiment agreeing to something like 14 decimal places. So even if it is quantum, there is still some serious hope that we could actually investigate this using the tools of physics that we employ in laboratories and in our brains as we do study these things. Here's applied Maxwell's equations. This is an old 8036 microprocessor chip from Intel. Here's a wiring diagram. Here's a tiny fraction I got from Nick Spitzer at UCSD, a very well-known neurobiologist, of the connectome, which is a map of how different processes in the visual system connect to one another. It's color-coded, and you can't read it, and even I can't read it up front. But the idea is that, look, these things look the same, and maybe at their heart have the same underlying phenomena at work, Maxwell's equations, maybe even quantum mechanics, that's okay. But should they be amenable to study using the laws of physics? And I'd like to think the answer is yes, but of course many of you are much more expert than I am. So when you think about these things, when I talk to a non-expert, they always want to know things about the soul, the spirit, the self. So I helpfully found this diagram here. Okay, so that's where you are. That's where I don't know where that is, but it also looks a lot like the cosmos, doesn't it? And then if you want a slightly bigger perspective, we can look, zoom out a little bit. Okay, so it's really depressing to me that probably 99% of you guys in the audience, cannot find where the Earth is on this plot. Okay, that's depressing. Okay, you can't see it. So this is meant to represent the Milky Way galaxy. It's not a real picture. It would take too long to get out there. But what I'm going to talk about today is not the stars themselves necessarily, but the space between the stars. I'm going to start talking about that, the emptiness of space that appears empty, but is not so empty in many different ways that have great consequences to the study, at least of the implications of cosmology and early universe physics, on the way the deep future may evolve, and potentially on the notions of free will, Boltzmann brains, and things like that. So that's the motivation. So let's take a cosmic ego trip. Ivette talked about the opening of this glorious new epoch. We are like Galileo. We're living in Galileo's time, I should say. And that Galileo opened up the heavens to the investigation of astronomical phenomena using his eyeball, his refractive telescope in his eyes, connected to a telescope tube he called a perspeculum, that gave him perspective, telescopic vision, distant vision. And he used this, as is well known, to overthrow the pre-Aristotelian doctrine that the Earth was the center of the solar system, which was effectively the universe to the ancients. So in doing so, he created a great deal of controversy. And the way that he did that, he actually didn't prove Copernicism. It's a fallacy to believe that he proved Copernicism. What he did is he showed that there's not one unique center to the solar system by observing Jupiter and observing the phases of the planets. So there's some phases here. This is Venus, exhibits phases, and they can only do so if it's closer sometimes to the sun than the Earth is. He showed that Saturn has these weird ears. We now know what those are. But the clinching evidence were his observations of the planet Jupiter. And he did something that I do to this day. He named an astronomical discovery after the donor that funded his experiment. Okay, so he named these satellites. He named them the Medici stars after Cosimo de' Medici, who was his patron essentially, who was his national science foundation. And with this theory, put forth originally evidence only in the visual form in Sidereus Nuncius, a great book. Ivette, you should get it from your son before you leave. I'll give you a copy. Because this book really just laid out visual evidence. And later on, the Dialogo and the dialogue on two world systems, then he laid out the evidence for heliocentrism. And that's really what got him into trouble and got him put before the Holy See, which is the Inquisition, basically. But this is a wonderful book, and it's worth a read. It's really the first scientific text of its kind. He's the first astronomer. He also did the first measurements on what's called relativity. And he was really driven by a passion to falsify the Aristotelian theory, not prove his own theory. And that's where you get into danger of what's called confirmation bias. So he constructed a universe that's centered on the sun with the known planets that were known at the time. Notice we named the days of the week after these planets. And astrologers had done that for years, and it was only until later when Herschel discovered the planet Uranus that there came this question: do we add another day of the week for Uranus? And some people aren't comfortable pronouncing Uranus. They do it the wrong way. So they didn't add another day to the week. But nevertheless, this was the new solar system, which effectively was the universe, no longer centered on the Earth. Matching observations, falsifying previous models, not proving it, but motivating it. I challenge you to think about how you could prove that the Earth is not the center of the solar system. Not prove that the Earth is the center of the solar system, or prove the sun is the center of the solar system. It's very difficult to do. But actually, it can be done, obviously, or we wouldn't know about it. Now, Galileo did many things, but he was not immune to the pernicious effects of what's called confirmation bias, in that he had a theory now that he wanted to motivate in greater depth. So he looked at everything through the lenses, if you will, of the Copernican theory. And he looked wherever he could find evidence of Copernicus's model being correct, and he even fit some things to that model that were incorrect. So everyone's heard of Einstein's biggest blunder, although some say it's apocryphal and made up by George Gamow as sort of a joke that he said when he added the cosmological constant. He called that my greatest blunder. It's not clear. There's a book by Mario Livio called Brilliant Blunders that debunks that particular myth. But nevertheless, heroes make mistakes. Einstein makes mistakes. Galileo made mistakes. And here it is right now. I'm going to give to you what I think as an astronomer what his biggest blunder was. And it's a pretty good one. If I'm lucky enough to make the blunder that he made, I'll be quite excited about myself. So this is a constellation, a fraction of a constellation called asterism. It's called the Pleiades. If you're Japanese, you'll recognize it as Subaru, which means the united. And they're united because they kind of look like they're all clustered together, and they blend together in a milkiness. And it appears to the eye like a milkiness. So soon after Galileo sketched the moons of Jupiter and phases of Venus, he sketched what the Pleiades looked like through his perspeculum tube, through his telescope. And what he did was beautiful. He illustrates, just by drawing, what the graphics, what the physical perception was in his mind. How did it feel to experience looking at these stars through his telescope? He did that on the cover of Sidereus Nuncius, as you saw, the big craters that don't really exist on the moon, but it's the perception that mattered to him, because there was no World Wide Web. He only printed like 100 of these things. The ones that exist today are mostly fakes. But what he shows here in these stars of David, these open stars, those are the 6 stars. They call it the 7 sisters, but really only 6 stars are particularly easy to see. These stars of David, these open stars, are stars that you can resolve with your eye, that you can see without the aid of a telescope. But with the aid of the telescope, you can see innumerable stars, all these black filled-in stars. Those were stars you could only see through a telescope. So what he says down here is, what was observed by us is the nature or matter of the Milky Way itself, with the aid of the spyglass may be observed so well that all the disputes that for so many generations have vexed philosophers — I love the way he teases philosophers, as all physicists do nowadays — are destroyed by visual certainty, and we are liberated from wordy arguments. Okay? So he's saying visible certainty. The eye, connected to the brain, and the visual connectome, that can prove things in physics. It's amazing. Unfortunately, evocative as these diagrams are, they're not correct, and this led to his greatest blunder. He claimed, this is the Hubble Space Telescope looking at the Pleiades, at this nebula, and it turns out it's a nebula, which is Latin for cloud. And he thought the nebulosity, he was saying the nebulosity was just many, many stars that he could not resolve with his limited size telescope. It was only about 1.5 inches in diameter. So he said, if I had a bigger telescope, which he went on to build, but he said, if I had a much bigger telescope, I'd see this fuzzy milkiness, and that would be the actual stars that I couldn't resolve before, just like this one, this one, and this one are. So in his desire to show that stars are just like stars like our sun, and the whole Milky Way is made up of stars, he committed a blunder. Okay? Again, not a great blunder, but if you zoom in on this star down here called Merope, this lower star here, and you zoom in on it, you see now with the aid, if you happen to have a Hubble telescope lying around, you can now know that this is not ever going to be resolved into stars. In fact, there's no stars here at all, really. But what is there is dust. And dust reflects the light of Merope like little tiny mirrors. And what is the dust? The dust is reflecting the twinkling of the star. And it's primarily composed of iron and nickel. And I brought some here. That will be my gift. Oh, yeah. So it's basically like this. Much smaller versions of this. This is a meteorite. It's an iron-nickel meteorite. And the other things that are inside of that nebula are these things, which, if I found it, I got it off my 3-year-old this morning. It's a piece of dust. Okay? It's easy to find. I'd like to do laboratory experiments on my kids. So it's a piece of carbon, but actually it's a much purified form of carbon. They actually believe that the carbon in there is in the form of diamond, pure carbon, allotropically pure carbon. So that's a diamond in the sky. Isn't that cute? But what happened to that diamond dust? So that diamond dust, I claim, is us. This is a famous picture taken on Valentine's Day 1990 by the Voyager spacecraft. Carl Sagan turned the spacecraft around, pointed it at the Earth, where the Earth would be, and can you see it? Isn't it beautiful? It's a beautiful self-portrait. No, I can't even see it up here. I circled it here. This image was called A Pale Blue Dot, and he made this beautiful poem that went along with it. He said, we succeeded in taking that picture, and if you look at it, you see a dot. And then he goes on with beautiful prose. He says, that's here, that's home, that's us. Every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam, just like we saw it with Merope. So dust is real, and the dust becomes us. This is the planet suspended in the sunbeam, just as it was for Merope. Now, in the 1700s, the successor, the heir to Galileo, was William Herschel, a proper British gentleman, who had an enormous telescope, the 40-foot telescope, in the countryside of England. He made a map of the galaxy that basically overthrew the Copernican revolution that Galileo had ushered in. He put the Earth at the center of he put the sun at the center of our Milky Way galaxy. What he didn't know is that he was being deceived by dust. Dust attenuates the view in all directions and makes it appear that stars which are close by in different directions are actually much farther away than they are. And that optical illusion is a mirage, for we are nowhere near, as you saw in the beginning, we are nowhere near the center of the galaxy. We're about tens of light years, of thousands of light years from the center of our galaxy, where a giant Milky Way galaxy spirals around a black hole, the mass of several million stars. And that was discovered by Herschel and Curtis, and then Curtis and Slipher, and Hubble actually disproved that we're the center of the galaxy. Now the question today is, are we the center of the multiverse? So to talk about the multiverse, I have to talk about a different type of telescopic evidence. So we see light, as Ivette said, we see light primarily since Galileo in our telescopes. But it's not all light that we can see. Some of the light we see is invisible, or we detect is invisible in the form of microwaves. This is the famous cosmic microwave background radiation, roughly 3 Kelvin thermo black body signal that arrives to us in all directions, almost uniformly perfectly. So Penzias and Wilson measured this in 1965, and they won the Nobel Prize about 13 years later. Nowadays, we can measure it, and if you were looking out on the Earth, this is what you'd see. Primarily, you wouldn't see any variation from this orange glow. So the question is, as Newton posed hundreds of years before Penzias and Wilson, in a universe of infinite perfect uniformity and homogeneity, how did clumps of matter come to form where they did? There's nothing that breaks the symmetry. So roughly speaking, for hundreds of years, we've been toiling under the assumption that the universe is too smooth for us to be asking questions as to why it is so smooth. So it's sort of a paradox. Later, we were able to see, as the galaxies and matter evolved throughout the universe, these dust grains collided and stars formed. This is the Hubble Deep Field. It's an image with about 5,000 galaxies in it. And if you take the size of this image, which looks big to you, but really it's only the size of this laser pointer spot up here if you go out in the sky and look at it. So if you take all these 5,000 galaxies, they're all compressed into a laser pointer spot that big. So how many total galaxies are there in the observable universe? All we have to do is count up those number of laser spots it takes to cover the whole sky. So we've got 15 minutes. No, I'm not going to do that. If you do that, you get about 100 billion stars. 100 billion galaxies, 100 billion stars in each galaxy. So it's remarkable. We think now that there are fluctuations. We don't know where these fluctuations came from. So we think that gravity pulls in the matter. The early primordial hydrogen and helium were the only materials that existed they coalesced in gigantic gravitational potential wells. When they got compressed enough, nuclear fusion took place, and they could ignite and become stars. The stars live out their lives over billions of years and explode, and they spew out into the interstellar medium surrounding them. They spew out chunks of rock and dust and iron. And that iron and rock and dust is what the Earth is, if you think about it. So this process takes us from shortly after the Big Bang to today. But the question is, how did those clumps of matter know where to form in the first place? So there was no real good predictive theory for that prescribed how that could happen until about 1980. So the cartoon you should think about is the Big Bang happened, then we see this CMB pattern, then stars and galaxies could start to form, and then we live in this present day today, 13.82 billion years after the Big Bang. But we care about what happened at time 0. That would be the most interesting thing as a cosmologist to unravel, and it has implications on the future of the universe and free will as well. So we can't go back in time any further using light. As we look back, it's like the unfortunate weather that we're enjoying during your trip to San Diego this week. We have June gloom has set in. So imagine that someone tells you a plane is flying overhead, or there's an explosion of a firecracker at SeaWorld, like there might be tonight or this weekend. Well, you could hear it, but you couldn't see it, because the marine layer obscures your view. That's what the CMB is for us. We have to use another form of radiation, and it's similar to the waves of radiation that Ivette mentioned, namely it's gravitational waves. But these are primordial gravitational waves, not short wavelength gravitational waves, the longest gravitational waves we believe would exist. And if you do that and you see them, you would know that a process called inflation took place. Now, I don't have that much time to talk about inflation, but I'll give you the cartoon version. The universe we see today at about, this image results from a time when the universe was about 400,000 years old. If you put that in seconds, it's about 10 trillion seconds after the Big Bang. Sounds big. It is big, 400,000 years, but it's not infinite. It's not really, really enormous numbers. Now, what we want to do is go back in time to the first fraction of a second after the Big Bang. In fact, we want to go back with inflation to the quantum universe, where it's purely quantum gravitational. And that's at an epoch of about a tenth of a trillionth of a trillionth of a trillionth of a second after the Big Bang. We believe at that point the universe can't be described by classical gravity and must be quantized, and we don't have a good theory for that. But if there were this fictitious field called the inflaton, or unknown, undiscovered field, I should say, then it would be like doing the following. Some of you are biologists. If you were to look at this object here, you could tell me what it is. Does anybody know what it is? Anybody need any more coffee? It's a blastocyst. Stuart got it, I think. So the blastocyst represents the way the human embryo looks at about 1,000 seconds after conception. I won't get any more graphic than that. Okay, so about 1,000 seconds after conception, this is what you looked like. Now, tell me, if you could look at this object in the future, what would it look like? Well, I'll help you out. I'll put some hints on it. So if I put some hints on it, okay? Now look here. Stuart, I took some liberties. I guess you're about 2 billion seconds old. It's about 60 years old, 59 years old. But 1,000 seconds to 2 billion seconds is only a factor of 2 million in time. I'm talking about 50 orders of magnitude in time. Much, much harder to do that. So we believe that inflation happened. This is a cartoon you should keep in your mind. If inflation happened, gravitational waves were produced. Those gravitational waves will make a specific pattern on the cosmic microwave background radiation called polarization. So the polarization has a couple different forms. I won't get into great detail about it, but it's just like these polarized lenses here, these polarized polarizers here, like your sunglasses that you would use on an ordinary San Diego day. Come back in July. Come back. Visitors Bureau asked me to say that. So these polarizers, when they're at right angles to each other, they obscure all the light. And that's the way your polarized sunglasses work, too. So we have to build a polarizing perspeculum. We have to build a telescope that can see things because our eyes are only very, very weakly sensitive to polarization. So I call this part the sixth sense portion of the talk. Now, it's not the sixth sense in the form of this fantastic movie, but it is the sixth sense which resides in a fraction of the human population can actually distinguish polarization naturally. And it's due to a remarkable aspect of our eyeballs, which are, as I said, little telescopes. So if you put a filter that polarizes in front of a telescope, you get a polarimeter. And that's what's used to measure these gravitational waves. But in your eye, you can actually do it. This is a phenomenon called Haydnger's brush. What I'm going to do is I'm going to remove this pattern instantaneously. And when it is removed, your eye sometimes, if you have the sensitivity, will still see the persistence of this pattern. And that's due to the fact that, that this pigment inside your macula, and Eric Vieri knows way more about this than I do, called xanthophyll, has a little bit of dichroism to it, a little bit of polarization asymmetry to it. So I'm going to remove the words. I'm going to remove the pattern. And raise your hand if you still see the pattern after I remove it. I'm removing it instantly. I'm not playing any tricks yet. So sometimes I see the opposite of the pattern, like the inverse of it. I see yellow where it was blue and vice versa. I'm going to take it away again. Anybody see it? Yeah. A fraction of the population can see this. We don't have the ability to see light with our telescopes. We need to see microwaves. So we built a microwave perspeculum, which is a short, really small telescope. It's only about 5 feet tall. It's called Bicep 2. It uses these very advanced detectors called superconducting transition edge sensor bolometers, and they're coupled to squid amplifiers. And I've got some up here, and I can show you guys later if you're interested. This telescope focuses microwaves that are polarized. From that, we make patterns of the sky as you would see them if you could see polarization of microwaves. Here's what it looks like on its mount. It's about 10 feet tall, weighs about 10,000 pounds. Has its own Twitter account, like everything has to nowadays. We took it to the South Pole in 2005. We installed it next to in the second most important building at the South Pole. And there we observed, and we're actually the longest continuously running experiment down there. We've been running nonstop since 2005. Now it's 2017. Quite proud of that. I've been there twice. And we measured a pattern that was consistent with the pattern you'd see if gravitational waves existed. And we got a lot of attention for it. It was on the front page of the New York Times. Even better newspaper called the San Diego Union Tribune. Pick up a couple copies. We also featured it. The Economist had an article, which I like because it says, "Man suddenly sees the start of the universe." So like some guys, whoa, the universe. Wow, that's awesome. Now, the question is, did we see what we saw, what we thought we saw? Or did we confirm a deeply held bias, potentially? And it turns out, unfortunately, it was the former. We were looking for a pattern. The signal looked just like the pattern we'd see, but we didn't know about the interstellar interloper dust at the time. There were no maps ever made of the sky at these frequencies. When we looked at the signal produced by dust and subtracted it from our data, the signal went away. So it actually burst this bubble that would have confirmed the existence of inflation. So that was disappointing. Here's just some images that I'm making about it, and I'll skip over those. Now the question is, how can we improve the measurements we're making of inflation to go deeper, to falsify it, or to prove it, or give evidence, I should say, rather, for it? So one way that we do it is our polarimeter at Bicep 2 is only sensitive to a single frequency, and to measure dust and the CMB, you need 2 frequencies. So we're now, with my Polar Bear collaboration and Simon's Array Cap collaboration with UC Berkeley, we're now building detectors that are intrinsically polarization sensitive and can measure 2 frequencies simultaneously. And that would help us instantly rule out the presence of dust. This is what the telescope looks like. It's much bigger. It's a Newtonian reflecting telescope, not a Galilean refracting telescope. That's in Chile. One last thing is about other pieces of evidence. Some people have claimed that you could spot the presence of another universe via a collision with our universe at early times, and that would then create a specific pattern of the CMB on the sky. And I give a little demonstration of this in a talk I gave for TEDx San Diego a couple of years ago. But the question is, in the multiverse, is it too crazy to be true? Because what it really predicts, I'm sure Sir Roger would say yes, what it predicts is that there's basically a functionally infinite number of universes. Greater than 10 to the 80th or 100th, 10 to the 100th, Google universes means that effectively could never tell a difference between that and a truly infinite set of universes. And that's called the multiverse. And it seems to be not only a prediction of inflation, but almost impossible, unavoidable, irreducible property of it. You can't get rid of the multiverse. So if you detect inflation, evidence for inflation, that mandates that we live in a multiverse. That mandates that there's probably 10 to the 500th or more universes that are not, some that are not dissimilar to ours, some that are exactly identical to ours. They're having this conference right now in a place called La Jolla. Some are having it in a place called La Jolla, okay? And then some don't exist for much longer than a nanosecond. So these universes can span a tremendous spectrum. The laws of physics can change. And what does that do to the very notion of falsifiability in a universe where anything goes? That's a big problem. So there are other alternatives. Sir Roger's proposed one. My friend Paul Steinhardt and Neil Turok proposed another one called the ekpyrotic universe. I won't talk about these except to say that they're cyclic. The problem that a lot of astronomers have always had with the Big Bang is that it implies a big banger or a beginning. And in fact, in the beginning, a lot of people were more attracted to the steady state model, which the CMB discovery falsified. And that was true because most cosmologists, like most people, are secular, and they found the notion of a single creation abhorrent. Now, I don't know if that influenced Sir Roger, but I know that many scientists prefer cyclic or eternal cosmologies because they avoid this question of what happened in the very beginning. Second problem, and just an homage to the other great film besides Anchorman that was filmed here, Free Willy. Okay, so what does this have to do with free will? Well, what if I told you that there's an infinite number of universes? Infinite, not just a big number, not 10, 20, not 500, 10 to the 500, or more. How would you know that you are you? That the perception of your own identity is really you? How, I wonder, what you are. How do you know what I am? So I've put up 2 pictures of Stuart. Now, who thinks, raise your hand, I don't care which hand, raise your hand if you think that, that these pictures are the same. Raise your hand. All of you think that they're different pictures. I've definitely flipped them around, I'll grant you that. But they're actually different. I put a little less twinkle in one of his eyes. I don't remember which one, but it's the same eye on both sides in the same one. Okay, so how do you know who you are? Why do we perceive it as who we are if there's an identical copy of this exact conference going on an infinite number of times? Infinite, not just once or twice. That would be scary enough, right? Okay, so the last things I want to say about the controversies in cosmology and consciousness seem to be parallel. They both have this question of origin. Explaining their own origin is very tricky in cosmology. And in the multiverse hypothesis, an eminent theorist, Paul Davies, he wrote that multiverse explanations are reminiscent of theological discussions. They invoke an infinity of unseen universes to explain the unusual features of the ones we do see. They may be all dressed up in scientific language, but in essence, they require the same leap of faith, faith being anathema to scientists. So that's a problem, and it's creating a great controversy in physics today. Last thing I want to talk about, I just have a couple of minutes left, are Boltzmann brains. This is the brain conference. This is the last problem. It seems to be inevitable that in most models of inflation, even without the multiverse, forget about the multiverse, that you get these organisms called Boltzmann brains, which they claim, this statement here said, where Boltzmann himself said in 1895, there are regions of the universe where there could be fluctuations, which he calls a galaxy, a whole world, in which consciousness and sentience could evolve. This is claimed to be a consequence of many models of inflation. So Sir Roger asked me to show a picture of a Boltzmann brain, so there you go. Very accurate, detailed scientific representation, a brain in a circle. But a Boltzmann brain is a hypothesized self-aware entity that results due to a random fluctuation, and it's due to the organizational principles that are more likely to occur for simpler structures than for more complex ones, as Sean Carroll's slide I stole from him. Now, there's actually a called Boltzmann lobotomy, because you can get rid of it in inflationary models. It seems to be inevitable, but Sean and his colleagues have actually gone through ways to get de Sitter, so-called de Sitter inflation, without producing Boltzmann brains. So I call that getting rid of the Boltzmann brain is Boltzmann lobotomy. So the last slides I want to talk to you about are just the consciousness controversies that I see paralleling and echoing the debates we're having in cosmology. Just as the appearance of something out of nothing can be explained by our saying that the first something was very small, cannot be explained by that, the birth of consciousness is rendered no less mysterious by saying that the simplest minds have only a glimmer of it. So speaking to the complexity of it and dressing things up in the seeming scientific language. Perhaps the emergence of consciousness is simply incomprehensible in human terms. Every chain of explanation must end somewhere. It's reductio. Consciousness might represent a terminus of this sort. Defying analysis, the mystery of the inner life of the mind may one day cease to trouble us. We'll just sweep it under the cosmic rug or the conscious rug. That's depressing. So I want to leave you guys with a gift. So how many of you have ever received a star or bought a star for somebody as a gift? Raise your hand. Okay, you should be deeply embarrassed. Shame on you, because these stars actually don't mean anything. I never look up and say, oh, there's Ron Johnson's star, yeah. No, we don't care about this as astronomers. But these guys are smart, right? They not only will sell you this star that no astronomer cares about for $99, but for an extra $14.95, you'll get a chart that shows a picture of it. So, okay, it's a pretty good deal. So I thought, well, in Roger's cosmology, there's an infinite number of aeons that preceded us. So why not sell off a couple of these aeons? So we started our own business, and see us after the discussion. So I just want to leave you with hopefully some motivation why you invited me and why I could go over by a minute. Is consciousness intrinsic? Yes. Is it something that's in the universe? That question I didn't answer, but I did talk about evolution of life via how dust became us, how Boltzmann brain processes might work, are inevitable consequences of cosmological models at the cutting edge, and do we have free will? That question intimately relates to the multiverse. And I conclude by saying it's not brain surgery, it's only rocket science. And I just want to say that for me as a scientist, as an experimentalist, I like to go out and measure things. So Feynman used to say, shut up and calculate, when theorists would worry about the abstractions of their theory. As an experimentalist, I'm blessed with the ability to go out and do measurements that have consequences on these wide-ranging things, even outside of my particular expertise in cosmology. And I'll leave you with the words of the immortal Mahatma Gandhi. He said, "The seeker after truth should be humbler than the dust. The world crushes the dust under its feet, but the seeker after truth should so humble himself that even the dust could crush him. Only then, and not until then, will he have a glimpse of truth." So dust is often overlooked, but should be never doubted. Thank you, guys. I present to Stuart a piece of space dust in token of my appreciation for visiting
I was hoping for an eon.
us.
Thank you
See
very
Roger.
much. I will treasure this, actually. Is there any evidence for inflation in the multiverse?
So the inflationary evidence, if you were to see inflation, a lot of people claim that there's inevitable link to the multiverse. You can't avoid the multiverse hypothesis. In other words, inflation takes place in this enormous petri dish we call the multiverse, and each individual colony or cluster or culture of bacteria is its own perception, has its own perception of being a unique universe, but until they come into contact, they don't actually know the existence of others.
Is that a yes?
If inflation is correct, the multiverse is correct.
Is
But
there
we don't know
evidence for inflation?
So what we currently have zero evidence for that inflation is guaranteed to occur. We have evidence that can potentially falsify the alternative models, but inflation is very flexible, and it may not be possible to falsify inflation. So I can't say it's not correct. I can just say we don't have evidence that leads us to inflation that's beyond a reasonable doubt, circumstantial level.
Okay. I don't know if Roger wants to comment, but I think he would disagree with that. Do we have any questions? Please be brief. We're a little...
I'm trying to answer the original question you had, is the universe alive or it's conscious? Just for the sake of argument, if we make the hypothesis that the self-induced motion or change is a necessary and sufficient evidence of consciousness, the self-induced motion or change, because we know from Newtonian laws, inanimate or unconscious matter cannot induce motion. So if we make that hypothesis, then the universe which has the spontaneous expansion and the motion built into, inherent in the universe, will that be sufficient to prove that the universe is conscious?
I don't know. I think, well, I mean, inanimate objects certainly attracts gravitationally and causes motion in other objects. Self-gravitational effects aside. And then second of all, is it possible that inanimate objects, I've heard certain stipulations that inanimate objects can have consciousness, panpsychism, something like that. I'm no expert in that, so I don't know that motion implies consciousness, but it does imply some notion of being measurable. In other words, motion does occur. If motion does occur, then you can measure time, and how time fits into all this, that's a big question.
Thank you.
Yep.
Thank you. I will go back to Stuart's question. So if I reformalize, you say that inflation implies multiverse, but inflation is not falsifiable. My question is multiverse hypothesis falsifiable?
Is the multiverse falsifiable?
Yes.
So certainly if, you could say there's no pink dinosaurs in this room, and you could go around and see, oh, there's no pink dinosaurs in this room. But if you're looking for evidence to falsify it, then it has to have some do or die test that it's predicting. The multiverse predicts everything. It predicts literally infinite numbers of where the gravitational constant differs by a part in 1 billion, and where it differs by 10,000 times what we see here throughout the universe, throughout its this multiversal space. So in a universe that predicts everything by the falsifiability criterion, it's so flexible it could accommodate everything. That's the argument of Paul Steinhardt, and the argument of others, I think, including Sir Roger Penrose, who claims that it's already falsified. So if we discovered incontrovertible proof for gravitational waves, that is consistent but not it's necessary but not sufficient to prove inflation. Inflation doesn't have a do or die test the way his theory does. His theory predicts certain observables in magnetic fields and patterns on the CMB. If we look for them, and some people have claimed they're not there. He's claimed that they're there. Some people have claimed they're not there. We're going to look into it with our BICEP 2 data. But the question of whether or not it's possible in principle to falsify the multiverse is what makes it so horrendous to many theorists working on it. But then there's Alan Guth and others that argue about it that say, no, it fits a tremendous number of observations very adequately, and we should keep it. There was just a letter signed by 4 Nobel laureates and 30 other scientists, including Sean Carroll, testifying that inflation is indeed the best scientific model. Not to say we're done and it's been proven, but it is. And so look up, it's called Cosmic Controversy. It's Paul Steinhardt and people like Alan Guth. Thank you.
Other questions? I have to say that many of us disagree with Dan Dennett in the quote he had. And in fact, I'll editorialize a little bit. The inflation and multiverse seem to me like what Dan referred to as a skyhook, referring to something magical that comes out of nowhere to solve all your problems. Right. So anyway, thank you. Are there any other questions in the back? Yeah, 2 more.
I had a question. What is your thought about the so-called holographic principle?
Oh, the holographic principle. Well, it's a pretty open-ended question. There are people much more expert in that than I am, and it's better to say little about that because it doesn't directly relate. It relates more to singularities and the properties of surfaces and areas to reflect the information contained within, and that there might be tremendous amounts of information that are possible to be encoded on the surface, if you will, the surface area of a black hole. And then Roger made very strong parallels to the properties of a black hole, along with Stephen Hawking, and the properties of the initial so-called singularity. So there are deep connections. It's a big question to get into. Lenny Susskind has a great book about this.
We better move on. Thank you very much, Brian, for a very exciting talk. Thanks for the gift. I really appreciate it. I really treasure that.
It was really fun. Yeah, it's a real meteor.
Okay. All right. I'm very pleased to introduce our next speaker, James Tagg of Sengen, the Penrose Institute. He's an AI, an inventor. He invented the touch screen on our phones. Thank you very much. And he will speak on, and he's the founder, one of the founders of the Penrose Institute. And he will speak on I have to say also, he's a tennis player, a father, and a tenor. He's a great singer. Maybe he'll sing for us. He will speak on, are humans computers? Zombies? Is the universe a computer? Do we live in a computer simulation? James.
Hi. Let's see. Is this working? You can all hear me? Great. Okay. So, yeah. So similarly to Ivette, I'm not going to talk about consciousness right the way through my talk, but my talk is fundamental to the question of consciousness. So if humans are computers, then we're zombies, just like Chalmers and Dennett and people say, and we have no free will. So it's important for me, when I look out the world, I don't think I'm a zombie. You might think I am. And I do think I have free will, and therefore I'd like to see whether I am a computer or not. And the question of whether I'm a computer or not is also quite interesting because it gives us some important factors about the universe. It tells us whether the universe could be a computer. And it answers one of the questions that a lot of people ask at the moment is, are we living in a simulation? Is this a simulation or is this the real thing? Why do I care about the computer problem? Well, at the rate of Moore's law at the moment, by 2053, computers are going to have more gates than we have in our head. So they would, in principle, be more powerful than us. And even if they're quantum computers, then by 2080, they would be more powerful than us. Now, it's not a quantum relativistic computer, as Roger is suggesting, but just a quantum computer. And then some of these prophecies that people like Wozniak comes out with, which is that we'll just be the pets of computers, might happen. I don't want to be a pet. Already, image classification is better than a human being. So a computer is better at telling arbitrary cats from leopards, better than we can do. But interestingly, you can kind of reverse engineer those machines and see what they're thinking. And this is a deep dream. And a group of scientists have then looked at these deep dream things and say, let's trick the computer. And so the computer thinks that that's an obelisk or a comic book or a soccer ball, right? We all understand that those images are not soccer balls or whatever, but you can trick a computer by just working your way through its classifier and persuade it. So that suggests to me that there's some understanding going on that we have that computers don't have. So I asked this question about whether we can prove that we're not in a simulation and that we're perhaps not computers. So if I just divide the audience sort of in 2/3, 1/3 and say, I'm terribly sorry, but I simulated all of you, right? These are the real people and you're simulated on my laptop here. And I projected them with a nice holographic projector so you don't feel uncomfortable. And all the usual moral laws work for you, so don't go running amok, right? Because you'll go to jail for the rest of your life in the simulation and so on. So be careful. Is there any way that you could sit there and go, no, I can demonstrate to you that I am not a computer simulation, a computer, I'm a real person? Is there something special about humans compared with computers? So to answer that question, we really need to know, well, a little bit, quite a lot actually, about computers. So computers were invented by Alan Turing. Oh, it's cut off. But invented by Alan Turing essentially in a field one day near Cambridge. And he was thinking about a puzzle which was presented by Hilbert, which is, can all mathematics be sort of processed by some automatic means, an algorithm? And he sat there and said, well, you know, remember when Turing was around, a computer was a person, right? A person went into a room and they wrote down long calculations and they computed. And indeed, Feynman's first job on the atomic bomb was a computer. He was there to calculate things out. He was a brilliant computer, you know, and could do all these things just in his head. And so Turing looked at this and said, okay, I think when you do a long multiplication, we could think of that as a tape. We could put it all onto a tape, and it would do these steps, step by step, and because it's a tape, he can treat it mathematically and prove things about it. And a nice thing about his idea is you could prove all sorts of things. So you could say, should I marry this person? Yes or no? And the thing would say yes or no and give you an answer. So it's a very nice thing. And then he came up with another insight, which is that there was a universal Turing machine. This is Stephen Wolfram's universal Turing machine. It's probably got to be the nerdiest tattoo in the world. So someone's actually tattooed onto the back of his leg a universal Turing machine, and that's the state diagram and the transition diagram for it. So in principle, you could take any problem in the world, any computer program in the world, and run it on his leg. I don't quite know how, but yeah, you could run it on his leg in principle. And that allowed him to ask questions about programs in general. Now, there's lots of different ways of specifying a Turing machine, and there's this thing called a Turing thesis, which is generally accepted but is not proven, which is that all computers are equally powerful. So Alan Turing's Turing tape is the same as Church's lambda calculus, is the same as D-Wave, is the same as if I made a clockwork computer or my Intel laptop, or certainly a lot of people think is the same as the universe. They're all Turing machines. They're all computing in some way. And then people say, oh, no, James, no. I can make something better. I can build a better machine. Look, all I'm going to do is I'm going to get lots and lots of Intel processors. I'm going to stick them next to each other, and I'm going to make a parallel machine. That is much, much more powerful than a Turing machine. And you go, well, no, it isn't, because I can take your parallel machines, those are the three on the bottom, and they're three machines, but I can reorder them, and I can have a single machine go 1, 2, 3, 4, 5, 6, and simulate all the parallel machines on a single machine. So in principle, it's the same thing. And then you make people say, oh, but randomness helps us, right? We get randomness in the universe, and quantum mechanics gives us randomness, and that's more powerful. But the problem is, as you go through your computer program and you branch and you make a decision one way or the other way, right, then it's the same as this parallel machine. Remember, the parallel machine runs every possible computer. The branching machine simply puts a random number in and runs one of the branches and ignores the other branch and saves a bit of computing power, but it's not more powerful. And then some people also say, well, the internet is more powerful than a general purpose, than a Turing machine. But you can draw a big, big circle around the internet and simulate it on a single computer. It would be very hard, but you could, so it's no more powerful. The universe could be a Turing machine, right? All of the laws that we currently know about the way that the universe evolves are unitary. And so as the universe bifurcates and splits apart, you could compute the various things. Now, you have a slight problem, which is that you're talking about continuous maths rather than discrete maths. And so you have to accurately model it. But provided you put 1,000 decimal places into your computer, you could model the universe. And it doesn't much matter that in some models of quantum mechanics, some of the universes go away, all the universes go away, there's only one real one, and in the other ones, there's billions and billions, or an infinite number of universes. In principle, you could compute it. So one of the important things to remember is that if I'm going to try and argue that I'm not a computer, it's no good if I run on the hardware of the universe, which is a computer. Because I could say, look, I have free will, I'm doing all this stuff, and I'm walking across this room, and you could go, no, I'm going to look under the hood, I'm going to see the clockwork, I'm going to read the instructions of the computer program, and I'm going to tell you what you're going to do next, because I can see the program that runs the universe, in principle. I mean, it's some sort of mythical demon that can do this, but it could, in principle, see under the hood. So it's quite important to me that if I'm not a computer, the universe can't be one either. So let's talk a little bit about the halting problem. So one of the things about computers, we said that they make decisions yes or no. Well, the problem is they don't make decisions yes or no. Annoyingly, computers do this thing called crashing. They blue screen, right? Anyone had that happen to them? No? Okay, so you get a yes or no or nothing, right? And this is pretty annoying. So Turing sort of looked at this and went, oh, that's very interesting, because maybe I could make a crash detection program, right? So he called it loop-free detection. And we now call it the halting problem. Will a computer stop with a definite answer, or will it just sort of hang like computers do? And a crash detector, a halting algorithm, would be very powerful because there's lots and lots of mathematics that you run it to infinity. So you say, are there an infinite number of prime numbers? And you go through and you iterate through and you count them. And if the thing would ever halt, if you had a halt detector, you could say, well, it halts. So if it halts, there aren't an infinite number of prime numbers. And there's lots and lots of mathematics that asks questions, are there an infinite number of things, including Fermat's last theorem, which is this, is there any other solution? If I go to infinity, is there any solution if I put 3 or 4 or any other number in the indices of that equation? So it would be immensely powerful, and we'll see how powerful in a moment. So again, I mean, this is one paper that Turing wrote that sort of invented the computer, worked out whether all numbers and all functions were computable, and solved this thing called the halting problem, which he didn't call the halting problem at the time. So he said, if there's a halting problem, a universal halting problem, so one algorithm that just, you feed it a problem and it says, yeah, that halts, that stops, it should be able to tell if it self-halts. Because if it can't tell itself halts, then there's at least one thing that it can't do, so it can't be universal. So it's typical mathematical proof. Can I prove a counterexample? And he used it using a diagonalization proof, which will take a little bit of time and so on to go through here. But there's a nice little flow chart that you can do today. And so you can put this flow chart together and say, if I give a program an input, and I have this imaginary halting procedure, and then if it's true, I halt, and if it's not true, I go into an infinite loop. What happens if I run it on itself? And it's a bit like the problem, this statement is a lie. If it crashes, it doesn't crash. If it doesn't crash, it crashes. So it gives you a paradox. And what that means is that the universal halt program can't exist. And I should say, lots of people kind of say, well, what is this like NP and equals P? And the answer is no. This is non-computable. There is no way of solving it at all. This is not just complexity. This is an absolute sort of absolute no. But though this proof is really an amazing proof, it might be a trivial proof, because you could have this proof work that almost everything is computable, and there's only one annoying little non-computable thing which you can never find. And therefore, the halting problem would be correct. There is no universal halting problem. But the things that don't halt, that mean that Turing's proof is true, are very rare. You know, you just don't find them normally. So what happened then was there was a sport immediately broke out amongst mathematicians to find things you can do and can't do. So you can obviously do addition, right? Addition is clearly computable, we can just see, and you can sort of prove it roughly and say, so 2 plus 2 equals 4, that's x plus y equals z, and so we can say for all x and all y there is a z, which follows the rules, and you can do it for everything. But very rapidly, people started coming up with things that are not provable and not computable. And so there's a thing called a partial halting problem. Let's say I took all of the problems known to man and I split them into 2. Could I solve A and then B? That's not possible, because otherwise you could use that to solve the halting problem, because you could iterate through it. You could do 1, then 2, I'm done, I've solved the halting problem. And that works for any arbitrary splitting. But again, it doesn't give us anything kind of to get our teeth into, right? It's just, you know, okay, you can't do it for some arbitrary split of sets. And then computer scientists looked at it and went, Rice's theorem, you can't prove any interesting, non-trivial property of a computer program. So that means you can never make a perfect virus checker. You can never run a program on a program that says it's a virus checker and say, do you halt for every virus? Yes or no? Because if you could halt for every virus, you could put every problem known to man as a virus and say, right, tell me, is this virus, which is actually sneakily Fermat's last theorem or the four-color conjecture or something we want to know, is this thing I've called a virus going to halt? And it would tell you, and you could solve the halting problem. So all viruses and all these sorts of things don't. And then mathematicians got much more precise about mathematical sets. But still, we want something concrete. We want something that you can't prove that a human has proved. Because we want to solve this problem, right? The problem I gave you at the moment. This part of the audience here is now kind of worrying, I might be a computer. Is there any way of telling? And it's a bit like the Matrix. We want something that we live in the Matrix. We sit in the Matrix, or at least you do, sorry. And you want to be able to run some program, some algorithm, do something that lets you out. And so we're going to go back to Hilbert to try and do this. So Hilbert had his 10th problem was, do all Diophantine equations have a solution? And Diophantus was a Persian mathematician, and he wrote a whole set of books, which we still have some of them, with these sort of mathematical problems in them, and he solved them. And they're just very simple things like, 4a squared plus b squared equals c. Is there a number that solves that equation? And Hilbert asked, is there a sort of an automatic way of solving all of them? And it took 50 years, but the answer to that question is no. There is no decision problem for those equations. There's nothing that will run and say, yes, that's solvable, or no, it's not solvable. So it's absolutely proven. Unfortunately, Fermat's last theorem is not a Diophantine equation. It's an exponential Diophantine equation. So we had to wait another 14 years for Matievich and a couple other people to prove that Fermat's last theorem is in fact Diophantine and is part of non-decidable mathematics. And then Andrew Wiles decided it because he found a proof for Fermat's last theorem. And if you find a proof for Fermat's last theorem, you have decided that it halts or doesn't halt, right? So there's a Diophantine equation that defines Fermat's last theorem. And if it ran forever, you'd have a proof, right? And he's found a way of showing that it halts because he's found a proof, right? You shouldn't be able to do that. So we have a paradox, right? We've solved a problem that shouldn't be solvable. Now, there's lots of holes in this argument, okay? So I'm going to have to plug some of them. In fact, I think I'll try and plug all of them today, my first attempt, okay? So, but obviously, you say, you're wrong, James, right? I can go to Google now, and I can type, what is the solution to Fermat's last theorem, return, and I get the answer, right? So it's clearly computable. There is a computer running on, Google runs it, and indeed Bing, Microsoft Bing will run it, and Yahoo, they all solve it, right? So it's clearly computable. So what are you talking about? You're talking nonsense. All Turing said is that you can't solve everything, right? You can solve things. You don't say anything. But that's not what Turing said, and it's not what Matievich said. What they said is that there is no solution to an arbitrary problem, right? There's no solution to an arbitrary problem. So what do we mean by arbitrary? Well, what we mean by arbitrary is you go up to deep thought, with a puzzle in your problem, and you go, right, I'm going to give you a puzzle, okay? Now, deep thought's a computer. It does not know what this puzzle is, right? So this puzzle is arbitrary. And I'm going to give this puzzle to deep thought and ask it for an answer. Oh, and I'm going to give it the four-color conjecture, right? You sort of thought I would give it the Fermat's last theorem, right? But I didn't. So it's arbitrary. I can choose any problem to give it. So the only way it can solve an arbitrary problem is for it to have some information in it that means that it's not a general purpose algorithm, it's somewhat special purpose. It needs some special information. And Matievich points out, even more strongly in his paper, that these types of Diophantine equations are each individually unsolvable by a general purpose program, and you're going to need ad hoc methods for every one of these. And what does he mean by unsolvable? Well, if you turn up, and he gets written to once a week with someone who says, I have a program that solves this, right? I have a theorem prover, right? I'm going to put an infinite number of problems in, and I'm going to just count through all the different problems, and it's going to say yes or no for all of these problems and give me a decision, because it's going to solve the problem, and a solution to the problem gives you a decision process. It's solvable, it's not solvable. And he says, well, you can send me a program in the email, right? And it will do one of 5 things. It will crash, it will go on forever when it shouldn't have, it'll give you the wrong answer. You say it can only give me halts or doesn't halt, true or false or something like that. They'll print 3. Computer programs do this, right? We expect them to do something, they blue screen or they print some complete garbage. And indeed, we said that it applies to sort of sets of problems. This is the first actual computer program that you can't prove. So this is a computer program that was come up with by Aronson and Yedida last year, and it's actually a proof. It tries to prove its self-consistency. And of course, it can't prove its self-consistency because of the Gödel argument, right? A theorem can't prove its own consistency. So it's a program that proves its own consistency if it halts, and you can't analyze it and say whether it halts or doesn't halt because it would cause a paradox. So there's an actual real example as opposed to just a sort of a set or an arbitrary program. So that's not arbitrary, that's an actual one that doesn't halt. So you then say to me, no, James, this is completely stupid idea, completely stupid argument. Andrew Wiles is a special purpose program, right? Not a general purpose program. He's a mathematician that studied from a whole bunch of PhD students over the years. He assembled all this skill. He is nothing like a special purpose program. What are you talking about? And I go, well, let's draw a big circle around the block of 4-dimensional space-time, right, in which all those mathematicians ever lived and any inputs or outputs or any use whatsoever to this puzzle are in, and let's simulate it on a computer. That computer should not be able to simply spit out solutions to these non-computable puzzles. Otherwise, it would be able to solve the halting problem, and we proved about 20 minutes ago that you can't do that, or at least Turing properly proved it 100 years ago. So that then puts, from my point of view, a limit on the universe. So the universe has 2 choices. It can either have enough information when it first came into being that it's super deterministic. It already has all the answers to all these puzzles baked into it. So that Andrew Wiles was going to go to his computer on that day, type those very things. The inkjet blobs of ink were going to go to the paper. They were going to, and then of course that leaves you with a question, which is, if that's the way our universe works, it's super deterministic, what calculated all that information? Right? So quite a lot of information to have lurking around the universe, and it must have been calculated somewhere. The alternative is that human beings are not computers, we're creative. Lucian Hardy from the Perimeter Institute came up with a specification for a quantum gravity or quantum relativistic computer, where he's defining the computer gates separated in space-time, and they're talking to each other, and they're quantum entangled. And that's a type of computer you couldn't model on a Turing machine. Remember, I proved earlier that everything's a Turing machine by simply saying I can model it on a Turing machine, so it's the same. So this is one type of computer that can't be modeled on a Turing machine and might have a little bit more power. So my argument is that humans are a little bit more powerful than a Turing machine. Not very much, because obviously if we had a lot more power than a Turing machine, then you'd get that movie Monsters from the Id, and we would be able to conjure matter from nowhere and travel in time and all sorts of things. It's just a tiny bit more powerful than a Turing machine, and they're therefore able to be creative and solve mathematical problems without, without having a super deterministic path. And therefore, we do have free will, and therefore there is a way for the right-hand side of the audience to prove that they're not a computer, and that's solve either the Riemann hypothesis or Goldbach's conjecture. And then we'll argue that you probably are not a computer. And that's it.
Thank you very much. Do we have time for some questions? We have a selection bias towards this side of the room.
But most people would agree that the abstracted word like red does not have the redness quality that I can experience. My redness quality just is. You can take an abstracted word like red and interpret it as if it was my redness or my greenness or whatever. But since all of the, at least in today's modern computers based on ones and zeros, are all not those ones and zeros abstract representations like the word red. You can interpret them as if they were red, and they can simulate red and everything, but they aren't themselves a physical red that I can experience. So since I can experience red, can I not move to that side of the room and say that I'm not at least a digital computer that's all abstracted representations that you can interpret as redness?
No, because I can install a color map onto Photoshop, right? And it will then tell me that things that are blue are red. And what I've done is I've basically given a lighting adjustment. So the problem you have when we look at scenes, and we say, well, that's red, and then someone shows that it was an optical illusion, it's actually blue, in comparison with its background, that's essentially a lighting adjustment that we run in our head. So you can play the same tricks with computers. You could tell me that. I go, no, you just Photoshop, mate. Try again. So the problem is you can report to me anything you want to report about what you see or what you think. I need you to do something a computer could not do in principle, as opposed to finds it a bit tricky to do or doesn't generally do or whatever.
I can ask a computer, what is your redness like? And all it can say is it's abstracted ones and zeros that can be interpreted as your redness, but it's not redness.
That is true, and that's the arguments about qualia, an internal feeling of being consciousness, which clearly I have and you have. But how do I prove from me to you that I'm not a computer and I haven't just been programmed to describe very precisely and well what it feels like to be read? But I am computer, really. No, but unless I give myself away, surely I can just talk about color in the same way as you can talk about color.
Well, you'd have to see my poster to see how to F.
I'll absolutely come and have a look.
Hi, thank you. So if I understand your argument correctly, it's saying that since we observe humans doing things that we think computers cannot do, therefore the universe is not a computer.
Correct.
Correct. Okay, so I think I intuitively agree with this argument. I'm just wondering if it's necessary to, or if it would be possible to argue this in a much more simple way, like for example, any calculation involving pi, like just getting calculating the circumference of a circle from the radius or something like this is already an uncomputable problem because you have an infinite number of decimal digits, right? So
that is of course true, but given that we've only got another 1.5 minutes of questions, if I list out the decimal points of pi, right, we never get to a point where you can disprove me. And in fact, we never get to a point if we do this for the end of the universe. I just keep going, and there's never a point at which you say, you know, that you didn't get there. So unfortunately, anything to do with linear mathematics, you know, continuous mathematics, you can do to any arbitrary precision you want. It doesn't give you a proof.
But isn't that exactly the proof that it's not computable?
I sort of agree with that point in that it proves it's not computable by a digital machine, but you can't demonstrate that you're not me, that you're a computer and I'm not, or vice versa using that, because you'd need to do it, you'd need to talk digits to the end of the universe.
I guess my point is that anything that does this in practice, like a wheel rolling along a road,
that might be true,
is doing stuff that it couldn't be doing by calculating it. So it's just doing it. Physics is just happening.
I can make a simulation, and video games do all the time, that you can't tell the difference. You just can't, because I can do it to any precision I need to do it, and you can't prove it in a finite amount of time.
Okay, so
you can prove it in an infinite amount of time, but not in a finite amount of time.
No.
Thanks, James. Great talk. You had the two scenarios, the one scenario being superdeterminism, where the universe has all the information up front in order to answer all the questions, so it's highly computable. How does that change in a situation where you're not talking from like a big bang going forward, but more like the infinite eons that Sir Roger Penrose has been talking about? If you have an infinite universe where there is no initial condition?
I have no idea. That's the answer. I don't know how you would model that in, I mean, does information come through from one eon to the next in Roger's model? The photons come through. There are circles in the sky. So I guess if there are circles in the sky, there's information transferred between them. So, yeah, I mean, the question is, where did this non-computable information come from? You know, even in an infinite universe, where did it come from?
In that situation, would you have to default it?
No, I think you could do it either way. You're just left with the same puzzle, which is in an infinite universe with eons, what generated the non-computable information to allow us to do the sorts of non-computable things that we see do, to step outside the box and understand in Roger's sort of world.
One more, please be brief. We're over time.
James, I want to liberate this side of the room from having to do advanced mathematics. So have you thought about this kind of experiment? So as I understand Roger's suggestion, quantum effects must couple to high-level behaviors. So if you hook these guys up to EEG, and their EEG dynamics reproduced what you'd expect classically from a classical description of the brain, or if, on the other hand, we saw some sort of systematic, at a sort of statistical level of analysis of brain dynamics, some extra level of information coming in, we could deduce at least that these guys aren't a classical simulation.
Yes, so I think that I could stick a probe into their brains and see the brains doing certain things you wouldn't expect a classical computer to do.
Exactly. So you agree that that would be a valid experiment?
Yes, you could probe their brains.
Is somebody working on that? 'Cause
that's one of the things we're looking at in the Penrose Institute.
Excellent.
Yeah. Can you see it go on?
We have to move on. Thank you, James, for an excellent talk. All three talks this morning.